Hello friends, we shall start this video with a discussion about the magnetic moment of revolving electron in Bohr's model of atom. Say this is the nucleus and you have an electron revolving around this. Say this is the electron, and if electron is going in this direction. Now take any cross section. You know that the rate of charge transfer is nothing but current, right? Now, so I'll say that here there is a current because electron is crossing this cross section, and so amount of charge getting transferred is say E, the charge of electron, and this amount of charge is getting transferred in a time period of t. This is the time period, and you know that t is given by 2 pi r by v, where v is the velocity of electron. So from these two equations, what can I say? I is equal to E by 2 pi r, and here I'll get v. So this is the current, right? Of course, since electron is negative in charge, if this is the direction of velocity, then the direction of current will be this. Okay, hope everything is clear. Now, you know what is mu L? It is the magnetic moment. Uh, it is given by current times area, right? Of course, it's a vector, but now just consider this. So I'll write EV by 2 pi r into pi r square to get this as EVR by 2. This is mu L, okay? And the same equation, observe this, mu L is EVR by 2, right? I will multiply mass of electron and divide mass of electron. Why am I doing this? Because to write this equation in this form, E by 2me, and what am I left with? E by 2me is gone. Me Vr. Mvr is what? It is angular momentum of electron about the central nucleus. Yes, this is the relation between magnetic moment and angular momentum. Okay, and note that this electronic charge is negative. So if I write it exactly, it should be something like this. This negative sign indicates that the magnetic moment is in opposite direction to the angular moment. Okay, if you take some other charge whose charge is plus E, then it would have been something like this: ml by L is equal to E by 2me. By the way, this ratio of magnetic moment to the angular momentum is nothing but gyromagnetic ratio. And let's move forward. Of course, for an electron, this ratio is found to be 8.8 into 10 power 8 coulomb per kg. Hope everything is clear till now. You know that angular momentum in Bohr's model of atom is given by nh by 2 pi, where h is Planck's constant, that is 6.626 into 10 power minus 34 joule second, and n is a natural number, right? So you know the formula for mu L now. The least value possible is with n is equal to 1, right? So putting all these equations together, I can write it as mu L is what? Mu L is EL by 2me, EL by 2me, and I can write this L as NH by 2 pi. So if I put n is equal to 1 in the final equation, I can write this as EH by 4 pi me, right? This is the least possible magnetic moment for n is equal to 1. And if you substitute these values as E is equal to 1.6 into 10 power minus 19 and H Planck's constant as 6.626 into 10 power minus 34 joule second, mass of electron is 9.1 into 10 power minus 31 kg. You'll finally get the mu L minimum to be as 9.27 into 10 power minus 24 ampere meter square. And this value is known as Bohr magneton, and this is orbital magnetic moment. Okay, hope everything is clear till now. Let's move forward. Our next topic is galvanometer. I'll just try to give the rough idea about the working of galvanometer. This is the soft cylindrical iron core, makes the magnetic field lines radial and also increases the strength of magnetic field. This north and south poles of magnet are just to give this magnetic field. Okay, and this one which you see, actually this is the cylindrical thing, cylindrical iron core, and here you have this wire wounded in this way. There are many turns. Okay, and this is the top view. Just try to get some idea. And in last video or before last video, I've explained that When current passes through a loop and when it is placed in uniform magnetic field, it experiences a torque, right? And the torque is given by M cross B, where M is the magnetic moment. Okay. Now, for a single loop, it is current times area. Here you have many loops, right? Let the number of loops be N. So it will be NIA, where area is capital A, and it will be B. Don't worry, sin theta is anyways one here. So you have a spring here, which is in turn connected to some pointer, and here you have this markings. Okay, there is some mechanism. This spring provides a counter torque when this coil tries to rotate. The spring provides a counter torque and it is given by some constant times the angle deflected. Okay, where k is a constant. This should be equal to this torque provided, right? NIAB. So that you can measure the reading through this angle. More the deflection, more will be the angle. So you have the readings there. Hope everything is clear till now. So what can I write from this? This angle is nothing but NIA by K into magnetic field. So this is constant for a given galvanometer because uh, what this K is the property of spring and it is called torsional constant of spring, or you can say restoring torque per unit twist. So this K is a property of that spring and it's constant, and is the number of turns that is fixed, area is fixed, and current is what you have to read, right? Okay, everything is fine till now. There's something called as current sensitivity. It is the deflection per unit current, the angle deflected per unit current. So this angle by current gives you NAB by K. This is the current sensitivity. Okay. You know that galvanometer is used to measure only very small currents. Now what if I want to measure large currents? Uh, Galvanometer is typically used for measuring currents of some microamperes or something like that. So if I want to measure bigger currents, I have some other device known as ammeter, which works on pretty much the same principle. Actually, a galvanometer can be converted into ammeter. I'll tell you how. This is the galvanometer, say, and you have some resistance of the galvanometer. Let it be Rg. Okay. Now, the problem here is this can withstand only very small currents. So then what we have to do? If you have some larger current coming in order to save this device, you have to divert the current so that it takes what a division and very small amount of current goes through this galvanometer and large amount of remaining current goes to some other thing. It is possible when you have this arrangement. When you connect this shunt resistance, this is called as shunt resistance, and this is supposed to be very small. And if this is small, what happens? Much of the current which is entering goes through this path so that you have very small amount of current that is left to go through the galvanometer. And finally, this whole arrangement can work as ammeter. Okay, this is used to measure larger currents. Of course, the calibration is done in a different way. I mean, the guy who is giving this markings here, he writes different numbers there. I'll explain you. If that fellow knows that if I amount of current can give this deflection here, he'll calculate if I is coming here, what should be the amount of current coming here. It should be some I Rg by Rs, right? And he'll add these both. And finally, however, using this value of I, he'll calculate the total current that is coming from here, and he'll write that value here where the needle points, that value here, so that finally we see on the screen or on the ammeter, we see the current value that is coming from here. Okay, and that's what is the meaning of calibration. And the calibration of ammeter is done differently from the calibration of galvanometer. Hope everything is clear till now. And this ammeter, as you know, is connected in series in a circuit. There is something called as voltmeter that is used to measure voltage or potential difference, and it can be made just by applying some small modification to galvanometer only. This is the galvanometer, right? What you will do, the voltmeter, it has some what very great resistance which is connected not parallel, which is connected in series. This Rg is very large, so that Rg and R is even more large. This R is also large. So finally you have a large resistance here. Now why do I have a large resistance here? Because when you have a circuit here, say working with some R, I want to measure the potential difference between these 2 points A and B. So you know how voltmeter is connected? It's connected parallelly. This is your voltmeter. Here comes your voltmeter. Now, if this resistance of voltmeter is small or comparable, what happens is the net resistance changes, and you get different values of current and what resistance. So that's not your original circuit. Now it is something like you have changed the circuit. Now what is the advantage of having a very large resistance here? If it is very large, what happens? The net resistance will be R into R very large by R plus R very large, which is approximately equal to smaller only. So your circuit is not changed much. And of course, here you have this calibration done in a different way, such that you'll read the potential difference, and the principle is however same. And that's it for today. Hope you understood this, and keep watching.